All right, so let's go ahead and get started, continuing our study of implicit differentiation. So, someone to remind me first off, what does it mean to be in implicit form? What was the difference between implicit versus explicit form, more or less? So, sort of. So if we want to be a little bit exact, let's start with explicit. Explicit meant whenever I had, for example, y is equal to whatever in respect to x. In other words, I was able to isolate a single variable. Whereas in implicit differentiation, I don't necessarily have it in that form. I don't have an isolated variable. So the reason that we were interested in implicit differentiation is that we know that not every equation can be written explicitly. In other words, I can't always solve for one variable. But despite the fact that I can't always solve for a single variable, I can still try to get the derivative of that expression. So, and that's how we started looking at this idea of implicit differentiation. So here we're going to jump straight into example 5. Find the derivative dy dx, given that 3y is equal to x plus 7 over y minus 7. All right, so first off, clearly this equation is in implicit form. I don't have a plain y is equal to whatever. However, if I look at this, what rules do you think I'm going to need maybe in order to get the derivative? What rules do you think we're going to end up using? Yeah, it looks like here I can use a quotient rule because, well, there's a quotient. And that's still going to work out great and everything. But I'm going to try something a little bit different to see what's going to happen. So if I look at this, really there's not much that's stopping me from saying multiplying the left and the right by y minus 7, for example. So if I multiply the left and the right by y minus 7, technically I could write this as 3y times y minus 7 is equal to x plus 7. And if I want to do it a little bit nicer, let's go ahead and distribute this 3y, giving me 3y squared minus 21y is equal to x plus 7. All right, sounds great and all. Why might I be interested in doing what I just did here? Why might that help me a little bit? Yeah, in this case, whenever I rewrote it, then I'm actually avoiding a quotient rule. There's a little bit of a nuancing that I'll mention in just a moment. But whenever I write it in this form, it looks like I'm not worried about my quotient rule. In other words, when I look at this new equation, technically still the same equation, more or less. Let's go ahead and see what happens whenever I try to take the derivative. What's the derivative of 3y squared? 6y. Do I add, multiply by anything? Yeah, we write down a dy dx. Again, we just took the derivative of a y. Anytime I take the derivative of a y, I'm going to go ahead and put that dy dx immediately after. All right, what about the next part? What's the derivative of negative 21y? Yeah, we just have minus 21 dy dx. And then this is equal to, what's the derivative of the whole right side? Nice, we have a 1. Derivative of x is 1, derivative of 7, we got a 0. So I just did my implicit differentiation. In other words, we finished the calculus part of this. And now we just had to do the algebra portion. So I need to get dy dx alone. What can I do to get dy dx alone? So we're actually not going to add the 21 dy dx because we want all of our dy dx's to be on one side. So if I do that, I'm just splitting up my dy dx's. Any other ideas about what could I possibly do? Um, we can't exactly combine them because this one has a 6y and then this one's a 21. So I know, what was that? Yeah, we can take out any similarities. In other words, we can factor, right? In other words, here I have two different dy dx terms. I only want one in the long run. Both of these are saying times dy dx. I can factor out my dy dx, giving me dy dx times 6y minus 21 is equal to 1. Yeah, and then we can just divide by 6y minus 21, giving me dy dx is equal to 1 over 6y minus 21. Thus, I have an expression for dy dx. Again, notice that my derivative doesn't necessarily only have x's, it could have y's now. In other words, one benefit of this implicit differentiation is that to a certain degree, I'm allowed to play around with the original equation and then take the derivative. In other words, when I was looking at this, why do the more complicated quotient rule whenever I can do some quick multiplication and deal with a simpler derivative process? Yeah, if I did it this way over here, and I had to use my quotient rule, it would have low d high, we'd have a dy dx on the top somehow. There would be a lot of multiplying and stuff like that. Like I said, there is one little nuance thing that I'm not really mentioning here. Technically, they are going to be different derivatives, but those derivatives are in fact equal almost everywhere. All right, so we have our example 5, some practice with, further practice with implicit differentiation. Any questions about this example 5? So we're going to do a couple more practice examples of implicit differentiation before we move on to the next topic that's related to it. All right, so let me go ahead and clear this up. Let's see what I got next. Oh, nice. Find the slope of the tangent line at the given point. 7xy is equal to 4 at the point 1 comma 4 over 7. So this one's a little bit open-ended on how we want to proceed. So if I were to give you this problem, much like what I'm doing right now, what could be one thing that you could do here? We have a lot of different options. Well, first off, I know I'm going to be taking the derivative because we like to think the derivative as a general form of slope. But what's the first thing that you could do here? Again, there's a lot of different answers that I'll take. How? Well, we're not going to do that yet. Otherwise, we just get a number and a number, right? I know I want to take the derivative. Do I want to go ahead and just take the derivative right away? Is that an option? Why not? What's the problem with having a derivative be 0, though? We don't really have a problem with a derivative being 0. So what I'm going to say here is if I want to, yeah, I could go ahead and take the derivative. And then I'll do implicit differentiation. That's one way I can do it. The other way I might do it is, are we able to solve for y potentially here? If I'm looking at this, can I get y is equal to whatever if I want it to? Yeah, if I wanted to, I could divide by 7x on the left and the right, and then I get y is equal to 4 over 7x, right? And then I can do regular differentiation. So I'm just going to show you all the two different ways that we might approach this. First method is through implicit differentiation. This is an implicit form. We can go ahead and take a derivative. So on the left, if I want the derivative of 7xy, what rule do I need? Yeah, a product rule, because I have 7x times a y. So if I'm using product rule, I can say 7x is my first, and then y is my second. So y'all go ahead and tell me, what is the derivative of that product? What should I be writing down from the beginning? Great, so we have the derivative of the left. Because it was the first, we just copy down 7x. The second derivative of y is dy dx. Plus the second, I just copy down the second. Derivative of 7x, we get 7. And then this is equal to, what's the derivative of the right? 0. Great. All right, so I have this here. And for the sake of having a sort of clean answer, we can do this multiplication real quick, right? Y times 7, we get 7y. I'm just going to write that for the sake of making it a clean answer. Plus 7y is 0. So I've done my calculus so far. And now I'm going to deal with the algebra. I want dy dx. To get dy dx alone, only this one has dy dx. So we probably would benefit from moving the 7y to the right. In other words, let's subtract 7y. And we get 7x dy dx is equal to negative 7y. What's the next step for me here to get dy dx? Yeah, we can divide by 7x. So that would give me dy dx is negative 7y over 7x, which if you want to simplify it, my 7's can cancel each other out, right? At 7 on the top, 7 on the bottom, we get negative y over x. So I have my derivative so far. All right, so I have my derivative dy dx is negative y over x. But in the instructions, I'm not saying what's the derivative. I'm saying what is the slope at this point. So how do I get the slope of a line? Yeah, remember that the derivative is a function for my slope. That tells me I can plug in these numbers and it's going to give me the slope at that point. So all I got to do is plug in y and x. So the slope, if I want to use formal notation, the derivative at the point with 1 comma 4 over 7. This is just a fancy way of me writing, I'm plugging in the point for the derivative. Let's see, we have negative y divided by x. Well, x is 1. So negative 4, 7 divided by 1, we have negative 4 over 7. Giving me this equation, this slope here. All right, so far, any questions about how I got to my final answer, the slope of negative 4 over 7? Again, we got the derivative. If I want the slope of the line, I have to plug in my point. So I'm going to take an extra moment here to show you how else could I've gotten the derivative, for example. So I'm going to erase this left side. So in this first method, we went ahead and did implicit differentiation immediately. However, if I look at this and let's solve for y, I can do that by dividing by 7x on the left and the right from the beginning. We get y is equal to 4 over 7x. Or if you want to write it, we can write it as 4/7 x to the -1 power. That's still the same expression. Again, a negative power means I can bring it from the bottom and put it onto the other part, numerator to denominator or vice versa. So what's the derivative of this expression? We have dy dx. What's the derivative of 4/7 x to the -1 power? Seven times 0. So there's two ways you can do this. Either you can use the quotient rule here, or can we just use the power rule here? It's x to a power. So since that's just x to a power, we can do the power rule. Bring down the power. So we have -1 times 4/7. And then I reduce the power by 1. So to the second power. All right, so I have this here. I claim that this derivative will give me the same value as my other derivative. Is that true? If I plug in my point into here, do I still get -4 over 7? Yeah, if I plug in 1 for x, I get 1 to the -2nd, that's still 1. 1 times -4 over 7, I got the exact same answer. So this is to show you that a lot of times our derivatives, they may look different, but their values will be the same. All right, so any questions about that alternate method using the explicit form for my derivative? All right, so we've done a lot of examples about getting our, doing our implicit differentiation. So let's go ahead and move into, I believe if I time this right, our new derivative. Let's see if I have it right. There we go. So does anyone remember what that function is right here? Y is equal to, how do you even say that? So the first thing I'll note here is mathematicians have bad notation because this is actually not sine to the -1 power. I know it's weird because we have like the sine squared of x, but then this one's one of those unique things where different people came up with different notations at the same time. So we decided we'll keep this one a little bit different. So what I have here is actually the inverse sine function. Or in other words, you might have seen it written like this here. Y is equal to arc sine of x. In other words, the opposite operation of a sine, kind of like multiplication and division are opposites, addition and subtraction are opposites. Here we have the trig function sine, and you can either say sine inverse of x, or a lot of books nowadays say arc sine of x. It's the opposite operation. Yeah, the inverse. It's kind of like how we had square root and square are opposite operations. In other words, you can imagine that these are sort of canceling each other out. So we're going to be studying these, I'm going to call them the inverse trigonometric functions, or the arc trigs. So whenever we see this right here, y is equal to sine inverse of x, this is equivalent to me writing sine of y is equal to x. Because I can do sine of the left and the right, I get sine of y, sine and sine inverse are opposites, and I'm left with x on the right. So I've got this here. So my goal for this slide is somehow getting the derivative of arc sine. There's a reason that I wrote this on the right. The reason that I wrote this on the right is that we know how to get the derivative of a trig function, right? So let's try taking the derivative of the right side. So does anyone remember what's the derivative of sine? Yeah, we get cosine, or in this case, cosine of y times dy dx. Let's see if I timed this correctly. This one's just the formal thing of it. So if I look at sine of y equals x and I take a derivative, we get derivative of sine is cosine times dy dx. What's the derivative of the right side of this equation? Yeah, 1, right? Derivative of x, we get 1. All right, so I have cosine of y, dy dx is equal to 1. If I want to solve for dy dx, what do I got to do? For right here. How do I get dy dx alone? Yeah, we can divide by cosine of y. So I can divide by cosine of y, like what I have here. Yes, it is going to be equal to secant. Let's see if I have that on here, actually. We're going to talk about a triangle in a second. You didn't see that yet. So yes, I could change this. So I'm going to take this one step further. This derivative that I've written here has a y in it. I'm going to try to take the challenge of saying, how do I get rid of that y? And that's going to play into our triangle. So whatever's on the slide is actually going to be just the foundation theoretical background about how we get our derivatives that you're going to see here. So right here, first let me go ahead and pull up this triangle. So I have that sine of y is equal to x. In other words, if I take sine of an angle, I get this x value. So what I'm going to do is, let me go ahead and use a right triangle, because we know the trig functions are highly related to my right triangles. So if I label one of my angles y, because again, we have sine of y. Does anyone actually remember what sine is in respect to a right triangle, like the opposite, the hypotenuse, the adjacent? Yeah, so we have opposite divided by hypotenuse. Again, this is not something I'm necessarily expecting you to remember, but it's building the theory about how we're getting this. Well, since sine is always opposite over hypotenuse, like what I have here, and since that we have sine of y is equal to x, that means the opposite is x, and the hypotenuse is 1. Because again, we can write x as x over 1, so we can make the opposite of y be x, and the hypotenuse be 1. So I'm again going to be trying to pull out some old info that might be somewhere in your head. I have two sides of my triangle. I have this side, x, and this side over here, 1. How do I get the third side of a right triangle if I know two ends of it already? So remember that if I have a right triangle and I know two of the sides, we have this special theorem called the Pythagorean theorem. Anyone remember what the Pythagorean theorem is? Yeah, a squared plus b squared is equal to c squared. Again, this is just all notation stuff. So if for now I just call this a random letter, t as a placeholder, I have one side squared plus the other side squared is equal to the hypotenuse squared. So I'm going to try to figure out what this bottom piece is. If I look at this Pythagorean theorem and I want to solve for the third side that's unknown, I can subtract x squared like so. I move the x squared to the right. And then I can take the square root. So really, this bottom edge is the same thing as plus or minus the square root of 1 minus x squared. Or for our purposes, we're going to say positive square root of 1 minus x squared. So I did all these calculations, but what was the point of that? Let's look at my derivative. My derivative is 1 over cosine of cosine of y. What is cosine in respect to a right triangle? About the opposite adjacent hypotenuse deal. Yeah, adjacent divided by, adjacent divided by the hypotenuse. So since I know that cosine is adjacent over hypotenuse, which one of these three sides is adjacent to y? Yeah, square root of 1 minus x squared. What's my hypotenuse? Yeah, so that means cosine of y is the square root of 1 minus x squared. Therefore, I can replace that cosine of y with the x expression. Finally, bringing me to say, if I have the inverse sine function, the derivative in terms of x is 1 over the square root of 1 minus x squared. Again, I'll emphasize, I'm not expecting you to recreate this sort of proof, but this is just saying we didn't just pull this proof out of this derivative out of thin air. There's actually some background geometry in trig where it comes from. So I have the derivative of the sine inverse function. That is one inverse trig function. How many trig functions have we talked about before? 6. So how many inverse trig functions do you think there are that we're going to talk about? Yeah, 6. Good guess. So that means that there are 6 more derivatives that we will learn. And I'm going to give it to you in this next slide. Great. The 6 inverse trig derivatives. This is the one that we've just proven. And then now I have, oops, why is it cut off? I'll go ahead and fill those bottom ones out. Actually, that might be a good idea. Let me do this. Let me see if I can actually open up the slide real quick. Give me a second. Let me scroll through this. Why it's doing that. Let me just extend that down. Okay. That's very odd because it's reading it as text. Just give me a moment. Let's do this here. all of this. All right, that's not ideal. All right, so let me go back to the slideshow and I'll fill in as needed. So let's focus on these top four, and then I'll write in the bottom in a second. And then my thing is gone as well. Looks like I will write this on the board because the technology does not want to work with me. We'll try this one more time. Nope. It looks like the board is trying to tell me to end the class. There we go. And it's gone again. Let's go ahead and talk about these four on the top. And then I'll probably get to these other two on the bottom later. So the derivative of arc sine or sine inverse of x, whichever you want to say, is 1 over the square root of 1 minus x squared. The derivative of tangent inverse of x is 1 over 1 plus x squared. So if I look at these top four, why did I write them in this particular way? Why did I write these two on the left and then these two on the right? Well, I think I know what you're saying, but they're not really the inverses of each other. What do I know about the derivatives on the left versus the derivatives on the right? So if I look at this right here versus this right here, it looks like the exact same derivative, right? But one is positive, one is negative. And the same thing here for tangent and then cotangent. And notice again, this looks like the inverse cofunction. Sine, cosine, tangent, cotangent. This was supposed to be secant and cosecant. Oh, it came back. Perfect. So I'm going to fill in these blanks on the bottom. X squared minus 1 should be cosecant x d dx is equal to this. There we go. Derivative of secant is, arcsecant is 1 over the absolute value of x times the square root of x squared minus 1. And then we have a similar thing for cosecant. So we have 6 inverse trigonometric derivatives. Again, notice the 3 on the left mirror the 3 on the right. It looks like on the left we have 3 positive derivatives, and on the right it looks like we have 3 negative derivatives. Furthermore, we have the cofunctions each time: sine, cosine, tangent, cotangent, secant, cosecant. So we have these 6 inverse trigonometric derivatives. So I highly recommend that you keep these written down somewhere for reference. I'll give y'all any time to copy these before I move on to the last thing for today. And remember how I said I would ask you the derivative of each of the 6 trig functions randomly? I can do the same thing for this one now. We got some time to put it together.
So why is it that only for sine, cosine, and secant, cosecant that they can't equal positive or negative 4 or 0?
Well, whenever we look at, for example, the top row, what happens if you try to plug in 1? And then the same thing for this bottom one. And then if I look at the middle, is there really a number that's going to give me 0 on the bottom? Yeah, nothing's going to give me 0 for this middle row. That's why there's no restrictions on them. Basically, it's a long story short of saying I don't want to divide by 0. Mm-hmm. So I will be asking you throughout this week and through part of next week. I'm going to draw a random trig function or inverse trig function. And then I'm going to say, all right, what's the derivative? And then I'm going to see if y'all are prepared for that. All right, so let me go to this next thing. It gives me something to remind me of. We've done a ton of derivative rules so far. Let's go ahead and just list out all the rules that we've done for derivatives. So start throwing out some derivative rules or just straight up what the derivative is for a function. So anyone got any derivative rules that come to mind? Yeah, we got product rule, that's one thing. Yeah, we got power rule, chain rule. What else am I missing? Yeah, quotient. Quotient, that's an ugly U. Quotient. Rule. What other derivatives have we talked about? Yeah, we have the trig functions. Trig functions. We've got the inverse trig. Is there another one that we're forgetting? Involve what? Yes. That the exponential function, like e to a power. Exponential function. Function. So it looks like these are majority of the rules that we've talked about so far. Now that we have, let's see, 1, 2, 3, 4, 5, 6, 7 general groups. Tell me what these are. What's the product rule? Yeah, first d second plus second d first. That was my product rule. What was my power rule, give or take, in formula or formally? Yes. So power rule is whenever I add x to a power, I can bring down the power to the front and reduce it, subtract 1 from the power. Chain rule, we don't really have a nice way of saying that. Yeah, onion. Quotient rule. Yes. So remember, quotient rule is low d high minus high d low, all over low squared. Trig functions. I got 6 trig functions. Derivative of sine. Yeah, derivative of sine is cosine. Derivative of cosine. Yeah, negative sine. Derivative of tangent. Yeah, secant squared of x. Derivative of cotangent. Yeah, negative cosecant squared. Derivative of secant. Yeah, secant x, tangent of x. Derivative of cosecant. Yes, negative cosecant times negative cosecant of x times cotangent of x. We'll take a short break with the exponential function. What's the derivative of e to the x? Yeah, so y'all got it right. Derivative of e to the x is e to the x. And let's see if y'all wrote down what I just had on the slide a moment ago. Derivative of arc sine. Yes. Derivative of arc cosine. Pretty much the same thing, but negative, right? Derivative of, let's do arc secant. Yes. And then we know arc cosecant is pretty much the same thing, but negative. So I'm not going to ask that again. Derivative of arc tangent. Negative one? Yeah, it should be the positive one. So notice that I formatted the same way each time for the trig derivatives. I did sine, tangent, secant. I had them in the same format for both the trig functions and the inverse trigonometric functions. So the next thing I would talk about real quick is we've done a lot of trig rules. So not trig, derivative rules. As a preview for later stuff, are there any other types of functions that y'all know of that doesn't fall into these categories? Yeah, that we haven't really talked about the derivative for. Technically, there is one or two types that you may have seen before. Log derivatives. That's what we'll do later on. Probably not this week. But you got it right on point with the logarithms. We'll talk about what's the derivative of a logarithm. So yeah, all these derivatives, I highly recommend what I have here on the left, that you write them down on your little note sheet later on. It might be useful. And remember that in the derivative problems, we've done, again, 7 derivative rules. There's nothing stopping me from doing a combination of any of these. Like that. Yeah, exactly what was on that board before. Oh, a little bit of a coincidence too. This is going to be what I just showed y'all about arctangent. This is what happens in Cal 2 where you go the opposite direction. Arctangent, the derivative here is 1 over 1 plus x squared. We're in Cal 2, we'll talk about how do you go in the reverse direction. All right, so that's all for today. Tomorrow, I'll be asking the exact same thing that I said today. Give me all the derivative rules. And I want a recital. All right, besides that, I will see y'all tomorrow on Wednesday.